All right, in this video, we're going to be looking at trigonometric equations that are quadratic in form or can be solved using quadratic technique. So I wanted to just review briefly what you do to solve a quadratic equation in case it's been a while. Okay, so say you had, let me rewrite that right there. Okay, say you had the equation 3x squared plus 13x minus 10 equals 0, and you were trying to solve that. All right, remember, to solve a quadratic, you could use the quadratic formula or you could factor. Okay, almost all of your trig equations are going to be factorable. So I really want to just review that here, but go back if you need to or want to and look at page 712 in the text. You can get to that through Blackboard. Just go to the textbook button and look at page 712 and you'll see a whole review that goes beyond what I'm showing you here. So you should remember how to factor this. We did this at the start of class. When we were dealing with systems of equations, we had to work with quadratics. All right, so when we're solving this by factoring, I know it has to be 3x and x, but at the end, I need to get something that multiplies to be 10, and I have some choices. Okay, so maybe it's 10 and 1, so I might try 10 here and 1 here. That looks pretty good. Should work, but because I could get a 13, but they both have to be positive. And if I make them both positive, I can't get that sign to be negative 10. So I think instead of that, I'm going to use the 2 and the 5. Okay. And let me think a minute before I put them in there. If I put a 5 in this spot, that's 15x. And a 2 here, that's 2x. So I'd wind up with a 13x if I made the 2x negative. Okay, and this one positive, and the 15 minus the 2 gives me the 13x there in the middle. All right, now I'm going to wind up setting those factors equal to 0. Remember how we did that? Okay, and then wind up solving by adding 2, dividing by 3. Actually, I don't think you've had to deal with this. I just was in my mind running back through things in this course. And I don't think you've had to deal with a quadratic earlier in the course. So this is just the review you need. And so your answer would be those two numbers. All right, so let's see how that works when we have trig equations. So here's what you got to think about. All right, I have something that's something squared minus 3 times something plus a number. So 2 times something squared minus 3 times something plus a number. So I'm thinking it's going to factor. And what I do is I take 2 along with a sine x in this one, and then just a sine x over here. And that's how this first term comes about. 2 sine x times sine x would be 2 sine squared x. At the end, I know I have to have a 1 and a 1. So these have to give me what's in the beginning, and these have to give me what's at the end. Okay. All right, so that looks good. Let me see if I can get the signs to work. I'd need them both negative so that I'd have a negative 1 sine x and a negative 2 sine x, and that's how I'd get a negative 3 sine x, and then the negative times the negative gives me the 1. Okay, once I get it factored, I'll do like I did on the other one and set each factor equal to 0, and then solve each of those equations. And this part right here, I'm feeling like you'll be okay with. So I want that to be red. 2 sine x equals 1, and so sine x would equal a half. Now you're not done though. See, you're trying to solve this for x, and you need to solve it for an x between 0 and 2 pi. So now we're thinking about, okay, where on the unit circle do we have an angle with a sine of 1/2? So we know x has to equal pi over, and to be 1/2 for sine, it'd have to be pi over 6. Okay, but we're only looking in one rotation, so you can just look at your unit circle to find it. But isn't that also going to happen when you're over there at 5 pi over 6? So you need to include that one as well. Now we don't have to do the plus 2n pi thing, just like we didn't have to do it. Well, I did have to do it on those. I shouldn't have done it on those. Yeah, I didn't have to do the 2n pi thing on this one because I'm only looking at one rotation. All right, and then here I need sine x to equal 1. So I think about where would the sign be 1? I'm thinking kind of about this unit circle, and I know it'd be right here. That's the only spot within one rotation where that happens. So that's going to happen when x equals, and that would be pi over 2. And we're only talking one rotation, so those should be your three answers. This, and that. Okay. All right, so that was one where you had to use a quadratic technique. You had to factor, and if you didn't come right out of an algebra class, you might be a little bit rusty on that, but I think you'll pick that one up pretty quickly. Okay. So we get pi over 6, 5 pi over 6, and pi over 2. All right, look at this one. This one's kind of interesting. It has a squared, so that makes it quadratic. But this one only has the trig function in one spot. So what you would do here is just add the 3 to both sides. So when you do that, I don't think I need to show that step. You'd have 4 cosine squared x equaling 3. Then you're going to divide by the 4, okay, here. So I added 3 first. Then I divided by 4. When I divide by 4, I get cosine squared x being 3/4. So now I'm going to square root both sides. Don't forget there's plus or minus on that side. And so I'm going to have, okay, cosine x equaling positive or negative square root of 3 over 2. So you want to separate that so you can think about it independently. All right, so let's think about this. So for cosine x to equal square root of 3 over 2, that's going to happen when this angle right here, when x equals pi over 3. That would be 60 degrees. That's when you're, no, that's backwards, sorry. Pi over 6. Because the cosine is the x coordinate, so it has to be the longer one. Oh, I said pi over 6, and I wrote pi over 3 again. So that's going to happen when x is pi over 6. But you got to think about the fact that you're trying to solve this within one full rotation. So you want to ponder that a little bit. You want to look at your unit circle, and you should notice that that's going to also happen, like I'm thinking about it like this. I know that I get square root of 3 over 2 for cosine when I'm up here, okay? And it's a positive, isn't it? Aren't I also going to get it when I'm over here? Cosine is the x coordinate, so I have to think about, well, what would this be? And see how that would be 1 short? That would be 1 pi over 6. I made that look not as good as I should have. Let me try drawing that again so you're really looking where you should be. Okay, pi over 6. There, that's better. Okay, so here at pi over 6, the cosine would be square root of 3 over 2. But if I went all the way around to here, wouldn't the cosine be the same? So I need to report both of those because I got to report every angle from 0 to 2 pi. So that's going to be there, or 1 short of 2 pi. Okay, so 1 short of 2 pi. So 2 pi, if I have a 6 down here, 2 pi would be 12 pi over 6. So I'm going to say 11 pi over 6. Boy, that looks terrible. So I'm going to say 11 pi over 6. Okay. All right. And then over on this side, I have negative square root of 3 over 2 is what I'm looking for. Okay, so those are going to be those angles that still have a reference angle of pi over 6, but the cosine is negative, right? So I'm still looking at those related angles. And so let me do those in a different color. Let's do those in blue, these guys right here. So this one happens when you're pi over 6 short of pi. So that would be when x is at not 6 pi over 6, but 5 pi over 6. And then also when you're pi over 6 past it, because see, all four of these have the same reference angle. So when you're pi over 6 past it, you're at 7 pi over 6. So I have 5 pi over 6, 7 pi over 6, then I have the pi over 6 and the 11 pi over 6. Those four. Okay. All right, so those are problems that were quadratic in form. So it's almost like on this one, I wound up using the square root method on this one. And on the previous one, I wound up factoring on that one. Okay. All right, so let me show you one more since this video is not too long. So what if you had to do a problem like this one? Okay, so what example am I on? That's example 6. Let's look at this one. Here's example 7. So what if you had something like 2 sine squared x minus 3 cosine x equals 0? Sometimes you have to use an identity in order to be able to finish up the problem. And see how we have sines and cosines, and there's no way to factor to get those isolated into two different factors? So sometimes you have to use an identity. So for instance, I can replace sine squared x. I can look at my identity sheet, and I can see that that's equal to 1 minus cosine squared x. Now, what would make me think to do that would be the fact that I had a cosine x over here in this other term. Okay. Then I would just distribute. And it doesn't get distributed to minus 3 cosine x because of the parenthesis being right there. Maybe put it in order with the squared term, that one that's not squared, the constant, and like I'm not changing the signs on that because I'm just rearranging them. So, but I'm keeping the sign that's in front of each thing. But I do not personally like factoring when there's a negative right there. So I'm going to go through and I'm going to change all the signs by multiplying through by a -1. So let me do that. What I did here and here is I multiplied by a -1, and that's always something I can do. So I like to do that because I can factor better when that's the case. Now, if these don't factor, you could use the quadratic formula. I'm just not expecting you to do that. Okay. So I would need a 2 here and a 1 there. Let me see if I can get another page without it spacing. Dang it. Okay, let's try this again. Yeah, there we go. Okay, so I'm going to try that. 1 and 2. Let's see now. I need it to be a +3, so I'm going to make that positive and that negative, because then here I have -1 cosine x, and here I have I have +4. Here I have -1 cosine x. So I would get the 3 cosine x, and I'd have the -2 I need. So I'm going to set each of those equal to 0. So on one side, I get cosine x equals -2. On the other side, I get cosine x equals 1/2. All right, so then I go to my unit circle and I think about this. I'm looking for an angle whose cosine is 1/2. And I want all the angles from 0 to 2 pi. I mean, all the x values from 0 to 2 pi. So I know that x could be pi over 3, 60 degrees, and the cosine would be 1/2. Okay. And then I also look and I think about it. So I'm thinking this would have a cosine of 1/2, and then I need it to be positive 1/2. Here's another angle that has the 1/2, but it would be negative. This would be negative, but in the first or the fourth quadrant is where I would have a +1. So I need to get all the way around. So this one is the pi over 3, and then all the way to here. Okay, so I have to think about what to call that. So it's this angle and this angle have the same reference angle. So it's pi over 3 short of 2 pi. So that would be 5 pi over 3. Okay. All right, so that's 2 of them. Now let's see what we get from here. We want to know, where does cosine x equal -2? And that's a never. Cosine x fluctuates between 1 and -1. So it never, you don't have any angle that reaches the -2. So you don't get anything from that piece. Okay, it's not possible. And so you only get the 2 answers. You get pi over 3 and 5 pi over 3. All right, so I went ahead and threw that one in, though it could go in a video that focuses on using identities, but I just thought it might fit well with what we've already done. All right, so I'm going to